So yeah, we were discussing the idea that the estimators that we were looking at um, can be viewed as approximating this regression function. This is an approximate regression function, which is the probability of y equal 1 given x is equal to x. They're approximating this as the form of local averaging. So you have these weights for any new data point x or feature x that comes in. You have this weight that you assign to each of the training data points. So I is the index in the data set, which let's say treated as a training set. So you assign weights to those data points for every given x. And these weights have some sort of a similarity interpretation, we'll see. In this case, they're going to be exactly 0 if, because you're looking at discrete features, if this particular feature, like in the training is xi, and the one that I'm going to try to predict is x, if they match, then it's going to be 1, otherwise it's going to be 0. So I'm going to look at all the training data for which their feature matches exactly my feature. And then this weight is basically like 1 over the total number of those. So it's like if there are 5 examples in the training data set whose features match the current one that I'm looking at, little x, then this weight is going to be 1 over 5. And then I'm just going to sum the yi's with this weight. So there are 5 of them. So essentially I'm averaging. So 1 over 5 summation of 5 yi's. So I'm going to average over yi's for which my current feature matches exactly those training features. And then later we'll relax this, and this gives a wide range of estimators. You can, if they fall into this category. Okay, and then so I'm going to come back to this multiple times. Any question about this? And then we talked about the way, like we evaluated the performance using the risk or the probability of error, let's say, or probability of misclassification. If we knew the actual distribution. But recall that we switched to the case of real data, so we don't have the actual distribution. So the question was, how do we measure the error or the risk in this case? And the simplest idea is that, okay, I had this probability of y not equal f of x. That was my risk for the particular f. So if I have an f, this is my true risk. So maybe I can just replace the probability with the empirical version using the sample that I have. So I'm going to replace the probability with the average over the training data. So if you're comfortable with the like frequentist interpretation of probability, so probability is really an abstract idea. Interpretation is like if you repeat the experiment many times, if you sample a lot of example, that's one interpretation. So if you sample a lot of data points, xi's, yi's, from P, so IID, then the averages of whatever event you want to calculate. So averaging over this matches the probability. So I'm going to average, sorry, this is not the probability, this is the indicator. So I'm going to average, so count the fraction of times basically, or how many times I observe that yi is not equal to f of xi, and then divide by the total. So it's the proportion of times that this event happens in the sample. And that's approximately equal to this if n is large. In fact, this is going to converge to that probability as n goes to infinity. If f is a fixed function, non-random. So the fact that that converges is very rigorous. It's like a rigorous statement of the fact that the probability is really like approximately these empirical average. So that has a name, that convergence. Anyone knows what that? So that average converges to the population. So suppose I have Z1 up to Zn, their IID from some distribution, let's say Q, doesn't matter. So 1 over n summation. So let's say they're IID and they have the same distribution as a random variable Z. I'm going to write it like this. So they all have the same distribution. I from 1 to n summation Zi, this converges in general as n goes to infinity to something. Anyone knows what this converges to? How many people have taken the probability course, 100A? So towards the end of that course, they talked about asymptotic results in probability. There are two main results in classical probability. What are those two? Central limit. Central limit is the second one. What is the first one? The easiest one. Law of large numbers. Law of large numbers. Okay. So does this resemble one of those? So law of large numbers, what does it say? You remember? Yeah.
If we collect enough sample, then our sample statistics will converge toward the population parameter.
Right. So sample statistic, what is the simplest? It's like the simplest statistic that you can think of. Mean, the sample mean. So it's a statement about sample mean. So this is the sample mean, right? If I have the eyes, if I take the average, that's the sample mean. So it converges to the population mean. So what is the population mean? How do you like write it? The population mean is the expectation. So I can write the expectation of one of them or expectation of Z if you want, or Z1, okay? So this average converges to the expectation of that random variable, right? So now imagine these are Zi's. So these are Bernoulli variables because they're indicators. So let's call this Zi. So this is an empirical average variable. It's a binary variable. And so it's a sample average, and the Zi's are independent because the xi, yi pairs are independent. So this converges to the expectation of like one of them, like expectation of Z1. And the expectation of a binary variable we've seen is just the probability that it's 1. Okay, so this is really the expectation of, for example, Z1 or any of them, okay? Or if you can't, you can call it Z if you want. So the IAD from X, Y. This notation, they have the same distribution as XY pair. All of them are from some unknown distribution. So if I call this Z, this is really the expectation of Z, and the expectation of Z is really the probability of it being being 1. So if you think about it, it's just an application of law of large numbers. Does that sort of make sense? Okay, so the training error for a fixed function converges to the true risk, the probability of error. Okay, and this is just a fact from law of large numbers. So if you forgot, just review law of large numbers, and this would be obvious, sort of. Okay. So if I fix the function f, then zi's are just independent. And their IID, they have the same distribution as zi or z. Sorry, this is not z. I made a mistake. So this is xy. Z would be here like 1, y not equal to f of x. Okay, so or you can just might be a little bit easier to do. Let's just do y1 x1, and this is really the expectation of indicator of y1 not equal to f of x1. It might be less confusing. So you can say this converges to the expectation of z1. Let's do it this way. And y1 pair x1 y1 is just a generic sample. This is also equal to this, because that's also what x and y, xy pair is also a generic sample. This is a little bit easier. Okay, questions? So this is called the training error. So why, I mentioned last time that this would underestimate the real risk. And in fact, if you look at the estimator that we did, like the plugin estimator, this guy basically can this is the estimator that goes into the optimal rule, which was, yeah, so, okay. So you do this estimate and then compare it with 1/2. So that's the sort of plug-in optimal rule. That if you go through the argument that we did, that's going to be the estimator that minimizes this training error. Okay, so if you minimize this training error under the 0-1 loss that we have, the estimate that it comes out is that. So it seems like everything is good. So I have this estimate of the risk, and I minimize it. That's my plug-in optimal rule. I can compute everything, and so we should be fine, right? But I mentioned something that why this is going to be usually a problem. Evaluating the risk using this would be a problem usually. So you remember, right? Yes, yeah. So the issue is right. The issue is when I minimize this, depending on how large the class of functions, minimizing over. So I really, if you minimize this, minimize over f. That's what I'm saying. So if I minimize f of xi minus. So I'm going to search over a class of functions. I'm going to introduce this notation so that you get comfortable with. This is like I have a class of functions. In our case, we have 4 possible functions. So I'm going to plug in every one of those 4 possible functions and then evaluate it and then find the minimum. So argmin, the function that minimizes this, that's going to be our f hat. And that turns out to be, turns out to be the plug-in optimal rule. Okay, so the issue is that in practice, I can, in this case, there are 4 functions, but in the continuous case, let's say, imagine it for a minute that we have a continuous space, then the space of functions is infinite dimensional. There are infinitely many functions. And then I can really find a function that makes this 0 for every basis. Basically, I can find a function that maps all the xi's to the yi's. And so I can make the training error exactly 0. And there are actually many functions. The solution is not unique. The issue is that I know that probably there's noise in the problem. So I don't want to exactly match yi. Some of these labels might not be might be sort of wrong in a sense. It's harder to justify it in this case, but there is noise in the data, and you don't want to perfectly fit the noise. So if there is noise, you want to sort of guard against that, and this doesn't tell you that. And what happens is, in practice, you will underestimate the real risk, because for the real risk, so they're like, I've seen like n samples, but there are infinitely many more samples as well. So you perfectly match these, but this might do a lot worse on an unseen example. Okay, and this really measures the average over all the possible samples. It's like the infinite sample rate, yes.
The reason it underestimates is because it overfits on the training data.
The reason underestimates because you purpose like in like deliberately minimize this risk. So that's so you're forcing it to be smaller. Okay, and so oftentimes it's smaller than it has to be. Right. And the reason is also, like, you can say overfitting. Overfitting exactly is this. Because you minimize this, you tend to get things for which this is smaller. Right. And the fact that it's smaller is that you overfit the data. If your loss is measuring like 0, 1 loss is measuring like agreement, when you minimize it, you also like overfit, fit perfectly to the training data, which is called overfitting, because you don't want to assume that there are examples. This is not always bad though. So modern machine learning, there are examples where you like tend to see overfitting, like it basically has 0 training errors and also good population risk. But the classical idea, let's say, especially in regression. In regression, you have, maybe see, or you have seen it, like yi is xi, let's say, plus noise. So I know that there is additive noise in each observation. I really don't want, or sorry, not xi, f of xi. Let's say f star. There's a true function that I'm trying to estimate. So regression example is f star of xi. And then if you try to minimize, usually you minimize the squared loss, not the 0, 1 loss. So you minimize yi minus f of, well, let's say f of xi minus yi squared argument. In classification, it's harder to see, and actually it's less severe overfitting. So when you minimize the squared loss, you're trying to match f of xi to yi. But if you really know that yi has noise, you really don't want to perfectly fit it, because you know there is a component of noise there. So if you perfectly fit it, you not only like fit this part, you also fit this part. And you don't want to fit this part. So if you fit that part perfectly, then you'd expect that in the future data, because that part is going to change, you're going to probably pay a price. These are heuristic arguments. They're not exact, but that's the idea. Okay. But the reason that I mentioned underestimate, because deliberately make it smaller, thinking about it. That's sort of clear. So the real thing that you want to do is this. You want to minimize this that you don't have. But then you have this, and this always, like, not always, but often underestimates. So what is the solution then? What is our solution? Is there a way to evaluate this risk, population risk, that's more neutral, like, let's say, unbiased? Anyone has seen any like real machine learning applications? Yes.
Use like a different loss function, like you use the altitude loss instead of minimizing square error.
Use a different loss function. So if you use a different loss function, you get a different estimator, right? So for different reasons, you might want to do that. Even in classification, I can use the L2 loss, for example. But that would change the estimator. It doesn't help you necessarily to evaluate the risk. So you want to also apply the loss here. Yeah, I'm not sure that would necessarily help. That would try to estimate the L2 loss. Let's say I want the 0-1 loss really. Right. And this issue so the actual issue here, like you see that, for example, why this doesn't work, because I'm saying as n goes to infinity, the law of large number should kick in and this should happen. But it wouldn't work for this one. The reason it wouldn't work for this one is that this f hat is not fixed. So if I fix the function as my sample grew, this would be a good estimate. This would be a consistent estimate in the language of statistic in the sense of each convergence. But because so this is true, but this f being a fixed function is true that I wrote there. If f hat is obtained by minimizing this, f hat itself depends on the training data. So this f hat is really, if you want to be careful, I need to write, so you'd see sometimes I might write f hat of, the function is right, like there's a x that I take in, but there's really a dn here, which is our data, our training data, x1, y1 up to xn, yn. So it really depends on the training data. Okay. You can see it easily like in this formula, for example. So this is like that, and the weight depends on everything, and then yi depends on everything. So when you evaluate at a single point, it also includes all the other training data. So it's really dependent on the entire data. Because it depends on the entire data, these terms, individual terms in that sum are not independent. Because when I look at the ith one versus the jth one, the xi, yi is independent of xj, yj, but the dn is like linking them. Okay, so there's the data, the entire data is not into f hat. So f hat is, they're both of them. So the terms are not independent. So we can't use the law of large numbers. Okay, because f hat depends on the entire data. Because f hat depends on the entire data. The terms are not independent. Even identities are independent. And the independence is really key. So cannot use LLN. Okay, so that's a real thing. So if I change the loss, this issue of dependence does not go away. Okay, I want to restore independence so that like law of large number kicks in. Okay, I want to add independent terms. So what would be the solution? Yes.
What do you want to be independent?
Individual terms in this sum. Right, because the law of large number requires you to sum like average terms that are independent, basically IID. Right. If I fix f, so this is like a fixed function, and so these are going to be just random because of xi, yi, and so xi, yi are independent, or IID, and so these terms will be IID. But when I plug in an f hat, which is constructed based on the entire data itself, these terms no longer are independent.
The training set and then like the algorithm.
Can you say that
Oh,
louder?
you have to show cells that you have not shown during the training set and then test it on that so you can get the risk out of those that were not in the training set.
Okay, so we have to, okay, so we have to show the algorithm example or samples that are not in the training set you said, and then provide them. So what was that you wanted to say?
Oh, yeah, well, I was just gonna say you could have like a training data set and then another split for like testing. Yeah.
Okay, split into training tests. That's what they do, and that's exactly what also was mentioned. So the idea is that you want examples that you haven't seen in the training. And assuming those are IID, those are going to be independent from F hat. Okay, and then once if I use that, I think that's a condition on the training data. By condition on the training data, this F hat is fixed. Now the randomness is in the unseen sample and those are independent. The condition on training data, I have the IID nature. So what happens is that I would do let's say another sample like tilde of size M, and let's say I gather a different sample of size M. These are different from the training data, which was without the tilde and N of them, right? And then I evaluate the function on my function, which is trained on, so I've had trained on the N, trained or like derived basically. Trained means like I constructed out of it the N, the way that we did. So we trained on the N, but we're going to test on this EM tilde. So I'm going to evaluate it on these examples that I haven't used in the training. And if these are independent, then condition on Dn, all the terms above are IID. So this is called test error, let's say. And this would be a consistent estimate of the risk. So as M goes to infinity, this is going to converge to really the risk of F hat. So I can consistently estimate. I get a consistent estimate of the risk of F hat. So all you need is like a different sample. And in practice, sometimes you have the entire data, so you have to construct your own. This is called test. So you have to construct this test sample or like unseen samples. You just split your data into two pieces. You put one piece aside for future. You don't touch it, and then you just train on the first piece. So you split your own data into two pieces, En and Dm. So train on this and then test on this part. Okay, so that ensures that the data points that go into this part are not seen in the training. And so you can restore independence of these terms when you average. Okay, yes.
So I have a related question to the last slide. So what do you mean by the model that minimize the training what do you mean by plugging
Plugin, yeah, so that's my name I gave to this estimator that so if you recall, we built an estimator, right? So there was let's go back. So this is sort of the optimal rule, if you recall. So the decision rule that minimizes the probability of y that will be given x. So this is the optimal rule. So you go back to the previous lecture, we built towards this. So this is the optimal classifier. In practice, we can't calculate it because we don't know that this is dependent on the conditional distribution of y given x, which I don't have. First, I assume that I know the joint distribution. So I have this conditional distribution. And then from this, I can calculate this optimal decision rule, which is sometimes called the Bayes rule. Bayes rule or optimal rule. But in practice, I don't have it. I can form estimates of the joint using empirical averages, again, by the law of background. And then we can also have an estimate of this. So we have an estimate p hat of this probability. And then this would be p hat, that f hat. That's what I call plug-in. Plug-in because I plug in my estimate of p in this and just calculate the rule. So that's our plug-in estimate or plug-in optimal rule. So that comes from this. So if you go back to these, that's how we estimate the joint. This is also by the law of large number. You can see it here. This converges to the probability, joint probability distribution. And so this is a good approximation of the conditional distribution. And I plug that into that formula, and that would be my rule. So that's the plug-in. I should say what I call plug-in. Or you can say estimate plug-in. Optimal rule. The one that has this here. Just plug in the estimate. And so if you go through the argument that we did, we really minimize the risk, but in this case, because I'm replacing it with this p hat, I'm really minimizing the risk with respect to this probability distribution, which is effectively giving me the training error. So if you follow through the argument why the optimal rule minimizes the base risk, you see that this minimizes the training error, because that's the equivalent of the base risk when we use empirical samples. So if you understand this, you understand most of the things that we discussed in the past two lectures. It's a very good exercise. Try to argue why this is. You can just think of this as, if you want, you write this p hat of f of xi not equal to yi, where this p hat is my estimate of the joint. This guy, this joint estimate. I'm really evaluating my error, like the risk under this probability distribution. So if you plug that in, so if you think of this as that, then what I'm really doing is I think you can condition, because it's a valid probability distribution, this p hat is a valid probability distribution, everything about probability goes through, so you can condition on x and then decide for that x what you should do. Sorry, I shouldn't do xi. Here it's just x. So what this is saying is assume that x and y are from p hat. Then everything that we did just goes through, just put hat on the p, and then we get this result. Sounds good? Or no? Any other questions? So this is what we usually do. Split into training. This called training test split or splitting. And it's the most common thing that people do in machine learning. There's another split, it's like train validation test, three-way split. So you can think of it as this training I might split into like a really training part and then a validation part. That plays the role of test because so you want to train your classifier, and then there's something that you want to choose based on the true error. So you want an estimate of the true error when during your training. And so what you do is really keep this part and then the validation set this, and you like evaluate the classifier on this part. This gives you like an estimate of the true risk during the training. And then you can use it to optimize your classifier. Once you're done, then you have a classifier. Now I'm going to just apply it once on the test to see like what is the final result. So this train validation test is often used when you do during training. You want to like have a prediction of the actual risk. So in order to be like consistent, you shouldn't use your training loss. You always have training loss, but training loss is not good. So during training, you also like split it into a piece. Don't touch it for your optimization. So usually you want to optimize, like minimize or like a loss. And so you do it on this piece that's not validation, and then you validate it. It's evaluated on the validation set. And then based on that, you do something like you do some operation that makes like minimizes this validation loss. And then by the end, you have it like a decision. You have a classifier that's set in the stone, then you just test it under this data to have it like report, okay? Sometimes you don't even see the test. Some people keep the test out for you and then you just publish a classifier, they evaluate it for you and then give you the result. Like, so that's the safest thing to do. Do not ever see it then. One word of caution is that if you have the test, you might have the tendency to train your classifier and do whatever you want and then test it and then go back and then fiddle with it and then go back and test it on this again and keep doing this. Keep using your test to evaluate the classifiers and then modify it. At that point, it's really not a test because you're effectively using it again to train your classifier. So all bets are off again. Okay. So if you do it like sparingly, it might be fine. But if you really heavily try to test it and then optimize again, this issue is going to happen. So you overfit to the test data as well. So it's the best if you want to do things to have a test data that you just apply once and in the end, never like use it during your training. If you want to do it during training, you can use it validates. So in this course, I'm usually not going to worry about the pre-data state. I'm just treating this test as a validation. Okay, because there's no final test for us. We do training tests. Okay. If you want to do anything, you do the test. But in practice, you usually do this, like train validation test. Sounds good. It's like one of the most important things to understand, I think, in machine learning. And it's not that easy. So this idea of overfitting is it's tricky. So for a long time, people thought if you drive the training error to zero, necessarily you're going to overfit and the test error is going to go up. But for like deep learning and some of these deep models, people observe that this is not necessarily happening. And that caused a lot of like surprise and interest in trying to understand. So, but the overall idea is okay. The overall idea is fine. You just have to understand first why in practice, like when in principle, it's not necessary that this is a good estimate of the risk because of the data dimension. Why, if you do the test, it is going to be a good estimate. But why in some cases it might be that even if we drive this down to zero, you're still as good. This is like a more advanced topic. It is not fully understood. But during this chapter, I gave you like hints of why that might be. So let's for now understand the classical picture, then at some point. So is this sort of clear? Why you do train test split? Why the training error might not be neither unbiased nor consistent. I think in the notes I have exercise. There's a statistical bias. So what you can ask, for example, is the expectation of this quantity the same as this? That's called unbiasedness. So I have an estimate, is the expectation, does the expectation match the actual thing that I want to estimate? Consistency means usually you have an estimate which is a function of n. Does the estimate converge in probability? Let's say to the true one as n goes to infinity. So if f is fixed, this is both unbiased and consistent. But if f depends on the training data, it's neither unbiased nor consistent in general. But if you do this, it becomes both unbiased. The expectation of this, like the condition of that kind of expectation would be pass it through the expectation. Each one of them will be the probability of error, and then m of them is just they have the same expectation. So the expectation would be a correct one, and it also converges, so it's going to be both unbiased and consistent. Unbiased and consistent. As m goes to infinity, let's say conditional on dn. So like tricky, but unbiased is without qualification conditional. Okay, that's training. That's validation. Any questions? Comments? So where do you get the test data? Usually it's split. If you have access to the data generating process, like if you're doing simulations, you're actually generating your samples, you don't have to split. So you have the training data, whenever you need new data, you just generate. Okay, I've seen people do this split, even if they have access to the data generating process, you don't need to do that. As long as you understand what you're doing. In simulations, once it's in your hand, then just generate more samples. But in practice, you can't. You just have this fixed data set. That's why you have to spare some part. Okay, I guess on this slide I used to evaluate. I'm gonna skip. So I think this data set I might probably share. So this is the entire Titanic data set is more. So okay, there's this many data sets. Sorry, there are this many rows. 1,309. I split it into these two parts. Let's say 982 for training and 327 for test. The 982 is what I showed you and what we built the classifier off of. Remember, we built the classifier based on these two. We calculated the training error. Actually, the training error is 0.22. That we have seen actually, because the numbers that I did was for the training. And if you do it on the test data, it turns out that the test error would be 0.217, which is very close. So in this case, actually, the training error is not bad. And the reason why it's not bad is your function class is very small. I pointed that out. So you really can't drive the training error to 0. Because you just have 4 functions, and with this many sample, you don't have a lot of leeway to actually drive it down. So because of this restriction of the function class helps you, doesn't prevents you from overfitting it. So it turns out that this happens in this case, which might also hint why sometimes overfitting might not be an issue. Okay. So I don't have much to say here. You have to just evaluate it on the test data. It's really easy. So you have a classifier, just go classify. Each of these, the classifier gives you the prediction, but you also have the true value, you just compare, and then count some of mismatches. So you test error. So generalization error. Generalization error is another name for the risk or the population quantity that we look at. Okay, so that P f of x not equal to y. So the test error is really an estimate of, you can say the risk, the statistician would call it a risk. Machine learning people usually call generalization error. Because we want to say how the performance generalizes to unseen data. That's the action. How the performance of that's our training and generalizes to generate unseen data. Okay, so it's just another name for the risk. And we have restricted ourselves for classification to this particular 0-1 loss, but you remember the risk is really expectation of the loss. So you can have a general loss function here. That's the risk. This is the risk. Okay, generalization is not bad. Any questions? So now let's get back to the more features. So I want to add more features, and I also mentioned this earlier. So let's say I want to add this P class. So this is going to be my X. This was a simple, this is going to be Y. This is going to be my X. Used to be my X. Now let's say this is X1, this is X2. So I'm gonna classify based on these two features. And I'm hoping that I'm gonna do better because I'm using more information. Okay, so collectively, this is my X. So X is now as a vector, sort of, or two columns. So how do we go about building classifier based on these two? P class is still categorical. That's three classes. So this is in 1, 2, 3. This is their passenger class. This has two values, male and male. So what is an approach? Can we like build the classifier here? Do I have to do anything special, or what we have used before? Like the ideas can still apply. How do you? Maybe do you recall what we did for this when we just had this feature? What did we do then? How do we build the classifier? That plugin optimal. Yes.
We get the probability of y equal to 0 or -1 given a combination of the x and
Right. So the rule, if you go through, is going to be the same. So you want to calculate the probability that y is equal to d or not equal to d given x is equal to x. You want this conditional probability. And for a given x, I'm going to maximize. So find the decision that maximizes this, or the decision that minimizes this. Okay. So argmax. We talked about this. If you review, it's the same idea. But x is now this thing. The thing to notice is, although it's like a vector with two coordinates, it's really another categorical variable with 6 levels. Okay, if you count all the combinations, female 1, male 1, female 2, male 2, female 3, male 3. So it's another categorical variable. Once you have two categorical variables, the number of you can think of it as a new categorical variable with the levels being all the possible combinations. Okay, so it really goes back to a single categorical variable. And so I just do construct a new categorical variable which has 6 features. Okay. Then I can compute the joint distribution, for example, which is going to be like y on one side, and then this new x, let's call this, I don't know, x prime, if you want. This x prime on this side. Okay. You'd have 0, 1, and then all these levels. And then you can compute the joint distribution by just empirical average. How many of the samples have y equals 0 and their combined covariance is this? And then you just fill out the proportions from your training data. Right? So you'd get a table like this. So this is really easy to calculate. So you go through all the training data, count how many have this pair of features. But like this response or this target and this pair of features. So about like 1 in 1,000 and so on. So you get an estimate of the joint probability distribution. From this, you can calculate the probability of survival. Y is equal to 1 given that X is a particular one. So that would be the regression function in our case. Okay. So I want to compute the probability, conditional probability, right? So that would be the probability that y is equal to 1 and x is equal to x divided by the probability that x is equal to x. So for example, if x is like I don't know, male 2. Okay, that's maybe like male 3. Then that's the joint, the probability of 1 equal 1, and that it's this divided by. So what is the probability that x is equal to 1? What is this? Yeah, you just add up those 2.377. And then it turns out to be something definitely less than 1/2. So I know the decision here, right? So that's definitely less than 1/2. So what should we do? Classify that. 0, 0. And then if you look at these, you would see the same idea. So it's going to be this divided by the sum of the two. So it's about like 0.02 divided by 0.1. 0.02 divided by 0.1 would be what? So about 0.02 divided by 0.1. What would it be? Like 0.2, right? So still like classify as 0. This one, 50. Like 49 divided by 0.049 divided by the sum of the two. Yeah, I let you figure this out. Okay, so you can just compute the conditional probability basically. If you just divided by the sum of the two. Right, and from this table we get that, and then you compare it with the 1/2 threshold. Right, does that make sense? This is the same procedure we did. If you go back, this is the joint distribution calculated from empirical averages. You can fill out this table. Hopefully, everyone can do this if you given the data. And then from this, I can compute the conditional probability. This is the regression function. Basically. I just need to calculate the survival probability because the other one format. And then the rule would be this is like estimate. Okay, so that's like if I want to be precise, this is my estimate. This is my estimate of the regression function, and the decision rule is really f hat of x is saying 1 if eta hat is bigger than 1/2, and 0 if eta hat is less than 1/2, and then if eta hat is equal to 1/2, you figure out in the forward what should do. So this one, for example, you can see it's like 0.1 divided by something which is very close to 0.1. So this is going to be a yes, like survive. This one is, let's see if I can survive. This one is tricky. Okay. But once you go through that, you would end up with, I can summarize the whole thing again in a decision tree. And these things, if you remember, are those conditional probabilities. Okay, so this is the conditional the probability of y even 1, conditional on nothing, but the base probability. So 38% of people survive. And then you go all the way down, and this is this is 0.99. So this is like, if you divide this by the sum, it's like 0.99. So that's F1. So female and passing to class 1, 99% of the time they survive. So that's like the decision is the one on top. So what? And if they're female and passing to class 2, the conditional probability is 0.87. You can calculate all the probability from the. If it's like female and passing to class 3, then it's 0.49. It's like below the threshold, and so you classify it here. For the male population, unfortunately, it doesn't matter. It's just everyone not survive. But there is a reason why this happened, but you can read about this story of Titanic. You probably know all what happened. I think the passive class doesn't make much. If you remember, the decision was like female survive, male not survive. If you don't add if you add the passive class, doesn't change the decision here. but it changes the certain female like branch a little bit. Okay. So if they are passing class trees, like they're barely below the threshold, so you get that. So you can see the numbers. So these are the conditional probabilities. And this decision tree just summarizes everything. If you stop at this level, we have our previous classifier. Okay, so that's like 0.19, if you remember, it's like the probability of surviving given that the meal is the probability of surviving. So at this level, I'm just classifying based on one feature. They go down, you can classify now based on this. So this is a very nice pictorial way of summarizing that conditional distribution at different levels and also the classifiers. At the base level, if you just stop here, you classify everyone that's not survived as the majority classifier. The majority classifier classifying the everything classified basis. Okay. And so you can have the three branches all the way. So the way the software does it, this is our part package. It just groups, it just split based on two, but here really it's split based on three. You don't have to do this grouping, but that's what it does in this case. So does that make sense? Yes.
What is the percentage represent? Is it the proportion of data?
Yes. So this last one is how many of the data like fall into these. So 1% of the data is there. 36% were female. 36% were female, and here 64% were male, and so on and so forth. Sorry. Okay. Any questions?
I think you mentioned in the last lecture, so like what if the conditional probability is exactly like 0.5?
Yes.
Is either decision fine?
So that's the homework problem. So you have to think about it.
Oh.
Based on so our if your goal is to minimize the probability of error, right? Go through the argument that we did, just for the binary case. See what you should decide. Does it matter or does it not matter? So you can see from the derivation that we did whether it matters or not. My goal is to minimize the probability of error. Assume that you know the actual final probability, like the P, you know. So you have to go to the derivation of our optimal rule and see if you understand how we did that, you understand what you should do in that case. Okay, any other questions? It's very unlikely that happens in practice, but if your data is like very sparse, then it would happen. If you have a lot of data, then it's like, so that one of the things statistically, does it matter? Are you doing 0.9 or 49 or it's like 0.5? This is very 0.5, and this is really not the conditional probability, this is our estimate of conditional probability. There's a margin of error. And the margin of error is large, then this decision is not really certain. And in this case, you can calculate. Well, I'm going to go a little bit over it. You're not going to do a lot of statistics, but a little bit of it doesn't hurt. So statisticians would worry about it because it's very near the boundary and our sample size is finite. The question is that maybe this is below the 0.5 because of error. Maybe it's really 0.52 in the population, but what happened there? So we have ways of dealing. So you're statisticians, majority of you, so you probably know how to do a test whether this is significantly different than like below 0.5 or not. Well, I'm going to talk about similar idea very shortly. Any questions? Okay, so this can be simplified. So this classifier is really like, if name, you stop here at this level. If female, we're going to do this and stop here. But really, I don't have this right here. I don't have to put it here. Okay, so it's really, um, if you do it, I do it with it. I did it with an option. I forgot what the option is to just go all the way. But if you do it with the default setting in the artwork package, this is what it is, which is like a simplified version. So this is different than the classifier that we had before because there's this split here. So it's potentially a better classifier. So now you can evaluate the training error, and you'd see that the training error is 0.219. The previous one that we had just based on 6 was 0.221. It's very close. And the test error is 0.211. The other one was 0.217. Again, very close. But now that I introduced another variable, the class of functions has become larger. So the number of potential classifiers is no longer 4, but much more. Does anyone knows how many classifiers I'm dealing with now? If I have like, basically I have a category variable of 6 levels. So I have a categorical value, potentially 6 levels, and I have a binary response. So I'm looking at functions that map the categorical variables with 6 levels to a binary response. This might be a homework problem, I don't know if it's signed it or not, but you can count how many functions there are. Anyone off the top of their heads know, like I want to like calculate the number of functions from a set X to Y. The cardinality of the set is X, the number of elements cardinality. The cardinality of the set is Y. In this case, it's 2, this is 6, but there's a general formula. How many functions? Right? 2 to the 6. Yes, because it might be a homework problem. Yeah.
Oh, never mind. I see before the cardinality of X was 2. So
Yes, it was a 2 to the 2. Yeah, it was hard to see which one of the 3 was, but yeah, this 2 is this 6. So 2 to the 6 is, what is it? 64. Is that right? So it's exponential. I can see like if I had like maybe 60 levels, then this would be 60. It would be 64 to the 10, which is very large. It quickly grows the space of functions. And then once your space of functions is large, then you have to worry about all the things that I mentioned. So then you start to like have potential for overfitting. 64 is still like maybe not too bad because you have like 1,000 samples. But by the time your number of functions is much larger than the sample size, then you have to start to worry. So what I want to mention, okay, now questions. I just want to do the statistic a little bit and then move on. Is this really statistically significant? So the difference. So I have now a better classifier apparently. So test error is 0.211. The one that just does it based on sake is 0.2117, like 2.7. 0.217. The error is in this digit, the third digit. So is it really that much better? So in machine learning, people fight over like these 1% of the improvement. So is it, can we like evaluate? So this is the simple classifier, this is the complex. Is the extra complexity worth it? Do I wanna, because I can always drive the training error down by increasing the class of functions, not always the test error, but in this case, it turns out, it seems like the test error also went down. It seems like we're on the good side of things. But is it extra, like this extra complexity worth it? And you can do a little test. You can do a little a statistical test, which maybe I briefly mentioned. So suppose I have, if you remember, these test errors are basically average of indicator value. So the test error was like 1/n. I'm going to condition on, let's say 1/m. I from 1 to n, indicator f hat of xi tilde not equal to yi tilde. So condition on condition on the training data. En. So now f hat is fixed, and then my samples are ID. So think of these as now Zi. This is like f hat 1. And then I have, this is M. Let's say I'm testing on the same test data. So I from 1 to M. And then I have f hat 2 of xi not equal to yi. So call these wi. So I have average of zi and an average of wi. So these are my two test sets. And zi's and y's are Bernoulli variables. They're binary and they have a certain probability. So the probability of this being 1 is really there is the actual, because that's the expectation of the probability. The probability, this is like the probability that this doesn't hold, or this is true, is the true risk. The zi, you can think of it as zi is like Bernoulli with probability, which is the true risk of f hat 1, and call it the p1. And the same for the other one. R of f hat 2. This is really P2. Okay, so there are these two probabilities which are really the probability of errors for the risk. And now I just want to compare the two averages. So assume my assumption is, let's say if they're equal, you can also test that P1 is bigger than P2. But let's say I want to say that should I reject the assumption that they're equal, that they have the same kind of error. So if I assume that they're equal, then well, first this is a good estimate of P1. So this is like as we mentioned. So this you can think of it as P hat 1. And then this you can think of as P hat 2. And then I can look at the difference. The difference of these is P hat 1 minus P hat 2. And if I have a measure of the variance, so let's say I have a measure of the variance, the standard error of this. So this is like an estimate. It has a standard error, right? It has a variance. The variance turns out to be, okay, so some issue is like, these are not independent. Because they're based on the same training. Here, I'm assuming that they are independent, but the calculation also gives you on the variance, so it's okay. But let's say pretend that they're independent based on independent test data. So let's say I have I split my test data into two parts. Tested one classifier and this, the other one and that. I have to divide this by like a standard error. And in this case, it would be approximately normal. So would be roughly normal. And then I can check under the null. So under the null, under the null, this P hat 1 is going to be roughly okay, P hat 1 is going to be okay, I think we're out of time. But the thing is that under the null, the mean goes away. And so this is going to be expectation 0. If I divide by the standard error is roughly normal. And then I can compare it with the normal distribution. Is it like consistent with the normal distribution or like much bigger? And if it's much bigger, then I reject the null that's there. If it's not much bigger, then I take it. I will not come back because we're out of time to come back and do this project, but you can think about this. I'm just doing a simple hypothesis test whether these are P1 and P2 equal. If I can reject it, then there's different classifiers. If I can't reject it, then say you don't have enough data. So probably stick with the smaller one. And I think the idea is that here we can reject those. There's not really enough data to reject the null that they have the same like population risk.